just a quick live stream on light. And I'm going to try to post the links that I'll be using. At least the main one is on screen, and the other two are just other things I've done about light. But there's claims made that light actually doesn't travel, that it has no speed, it's just there, right? But that causes problems in how we observe light behaves in different media. So I wanted to look at this article real quick because a lot of times, hey, Ryan Garcia, and camera doesn't work, and I don't know why. I've shut down other apps, but well, it does what it wants. Anyway, the problem is when I say that light refracts at a change in density, I never really went into why, and it has to do with speed because people think it's counterintuitive. But anyway, look at this little, there's a video here, excuse me, where it says the refraction is the bending of light. It can also happen with sound, water, and other waves. Whether light's a wave, this is a completely different question, but the thing is that some things are travel in waves and some don't. But anyway, the medium through which it's traveling, if that changes density, it can affect anything that's moving. And it says this bending by refraction makes it possible to have lenses, magnifying glasses, prisms, and rainbows. Even our eyes depend on this bending of light. Without refraction, we wouldn't be able to focus light onto our retina, which is true. I mean, if you've been to a physics class, I've been to many, this stuff is demonstrated. It's science, right? So, and in the video, they go into the illustration of somebody trying to spear a fish. You know, the fish is in water and the person with the spear is in air. And if you look at where the fish appears to be, it's not where it actually is because of the change in media for which the light is passing. And I'm not going to play that so I don't get copyright issues, but it says change of speed causes a change of direction when it comes to light or any EM wave, electromagnetic wave. Light refracts whenever it travels at an angle into a substance with a different refractive index or optical density. Good to see you, Mike. The change of direction is caused by a change in speed. If light is not traveling, this wouldn't be possible. And if it's not traveling, then what is the other explanation for this behavior of light or any other electromagnetic beam? For example, when light travels from air into water, let me get this screen where I need it to be. When light refracts when it travels at an angle at a substance with a different refractive index, this change of direction is caused by a change in speed, for example, of light traveling from air to water. How much does light bend? Here's an illustration of what they call an incident ray, which is your angle of view, basically. And it comes in at a certain angle, which they have this dotted line here called the normal. What's the normal? They'll define that in a minute. But angle of incidence is the difference in degrees between the incident ray, the ray that you're viewing along, and this normal line. And that's a 90-degree angle between normal and boundary between substances. Isn't necessarily air and water all the time, but the point is that if you draw a perpendicular line between two substances, you know, the boundary line between them, that's the normal line. Okay, and then the change in speed of the light has a predictable angle of refraction. And if you can see the relationship here between the angle of incidence in one medium and the angle of refraction in the other. Okay, so the refracted ray is that much different in its line. So when light travels from air into water, it slows down, causing it to change direction slightly. This change of direction is called refraction. When light enters a more dense substance, higher refractive index, it bends more toward the normal line. The amount of bending depends on two things: the change in speed. If a substance causes the light to speed up or slow down more, it will refract or bend more. Angle of incident ray: if the light is entering the substance at a greater angle, the amount of refraction will also be more noticeable. On the other hand, if the light is entering this new substance from straight on at 90 degrees, that is to say along the normal line, the light will still slow down, but it won't change direction. It's just how light and EM waves behave. And they give you different refractive indexes from low to high here. And the speed of light in that substance times 1,000 or 1,000,000 meters per second. So you can see the number goes down as the refractive index goes up. And the angle of refraction, if you say pick 20 degrees, it's just arbitrary. You can do their calculations and you'll come up with different angles of refraction. And you'll notice again, with the lower refractive index like air, at 20 degrees angle of incidence, it will refract 20 degrees. It'll be a 20-degree deflection. But if it's a higher index, it'll have a lower angle of refraction. All angles are measured from an imaginary line drawn at 90 degrees to the surface of the two substances. This line is drawn as a dotted line, is called the normal. Again, we saw that up here. There's the normals, the perpendicular line to the line between substances. If light enters any substance with a higher refractive index, such as from air to glass, it slows down. The light bends towards the normal line. If light enters a substance with a lower refractive index, such as from water to air, it speeds up. The light bends away from the normal line. A higher refractive index shows that light will slow down and change direction more as it enters the substance. And then a lens is simply a curved block of glass or plastic. There are two kinds of lens: biconvex, which just bi means two, so it's convex on both sides. It's thicker at the middle than at the edges. This is the kind of lens used for a magnifying glass. Parallel rays of light can be focused into a focal point. A biconvex lens is called a converging lens because they converge at the focal point. And you can see it changes angle twice because it's changing densities twice, one going from low to high and then from high to low. So it's changing angles twice, but it keeps bending the same direction. You would think that would straighten it out, but it doesn't, because this isn't like other things that, such as water, that seeks the least path of resistance. Light is not like water. And then a converging lens is, this is converge, is to meet at a point. Definition below: each light ray entering a converging convex lens refracts inwards as it enters the lens and inwards again as it leaves. These refractions cause parallel light rays to spread out, traveling directly away from an imaginary focal point. That means that once they hit the focal point, they keep going in their straight lines. So it's the point where they all converge is the focal point, and then they keep spreading out, and that's why it makes things look bigger. Then the opposite is a biconcave lens, thinner at the middle. Light rays reflect outwards and spread apart as they enter the lens and again as they leave. So they hit this at, they're going straight towards the substance, but it's thicker here, and because this is thicker, it's going to change the angle, and it's going to keep going away as it changes again. So the focal point is on the viewing side of the lens, is what's confusing, but that's just how light works. It's an observation. You can find pictures online where different kinds of lenses, and they'll have discrete beams of light, and they will do exactly, it's converging at your point instead of out here somewhere. So a concave lens, each light ray entering a diverging or concave lens refracts outwards as it enters the lens and outwards again as it leaves. These refractions cause parallel light rays to spread out, traveling directly away from an imaginary focal point. And refraction can create a spectrum. Isaac Newton performed a famous experiment using a triangular block of glass called a prism. I have some of those. I've demonstrated this myself with sunlight. And I have some videos about that on my channel somewhere. He used sunlight shining through his window to create a spectrum of colors on the opposite side of his room. The experiment showed that white light is actually made of all the colors of the rainbow. These 7 colors are remembered by the acronym Roy G. Biv. And why, I don't know. I must have clicked on something. Let me go back to where I was. Anyway, all the colors, these 7 colors are remembered by Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. And you can see here's the light coming in. Some of it goes, because light isn't always confined to a beam. Some of it goes off this way, some goes this way, but it splits at a narrow angle. That's the thing, is if you're using prisms, the sunlight needs to come in at a narrow angle. And then it will split into these different colors because of different speed changes. And each frequency of light goes at a different speed to begin with. And that's how you separate it out. When white light shines through a prism, each color refracts at a slightly different angle. Violet refracts slightly more than red. A prism can be used to show the 7 colors that make up white light. And Newton showed, and you can do this yourself at home too, you can buy prisms online anywhere, that each of these colors cannot be turned into other colors. They are what they are because of their speed. He also showed that they can be recombined to make white light again. So you can't split each of the colors that you already split, but you can put them back together again and it'll be white light, because white light is just, in similar way to sound, is a combination of many frequencies. Okay, that's why you can have red lasers or green lasers. They pick a frequency at which the light is emitted. Rainbows are just each droplet of rain is a little prism where light enters and reflects back at different speed, and you have change of density through each drop, which is why in order to see a rainbow, just from the sun, there has to be a lot of raindrops in the air and the sun has to be low. Otherwise, it's shining down. The rainbow effect would be beneath your feet on the ground. So that's why you don't see it. Anyway, it explains why you get secondary rainbows and all sorts of things. But the point is that light must have speed. Okay? Light must have speed. And as those other links I posted in the chat there that may or may not wind up under the video, I'll have to check. Sorry about issues with YouTube. That happens. I'm using StreamYard right now. I do that when I just have a quick little impromptu video to do. But of course, I will put these other links in the description. I'll try to remember, or under the video when I'm done. But the thing is that when somebody says light doesn't have speed, they need to account for these effects, which are observable, repeatable, predictable. You can vary the frequency of the light or split it into its frequencies and prove these things. So observation trumps everything else. It trumps theory. Now, then the argument is over waves and particles. But the thing is that, as I've explained in the other video and article that I posted, there are links to, that if you think of like a pond of water, if water waves, it isn't as though you have one molecule of water, it doesn't wave. It can't wave. Waving is something water does collectively when it's disturbed. If you have a collection of water molecules, like in a bowl or a pond or whatever, and something disturbs that collection of molecules, or that field, if you will, then it will wave in response. It will be more like a spring going back and forth, as I showed in the other video. And that's what we call waves. So a medium or field has to wave, but you can't say that water is made of waves, or water as an intrinsic value of itself, each molecule would wave. Water is made of discrete components or quanta called molecules. And they behave in certain ways when they're with other water molecules. Now, with light, the same thing would have to be true, that if it waves, then it has to have a field of light which is disturbed by something else. So light itself, in order to wave, has to be disturbed by something else. Hey, Soundlies. And we can't wrap our minds around it. It's where people try to come up with ether in space, quote unquote, because they're trying to account for a medium for light to travel in the sky. And whether you believe light's a wave or a quantum, it's demonstrable with the electromagnetic effect that light has quanta, or I don't like to use the word particles, but packets of something or other, packets of energy, whatever you want to call it, and these packets have spin. And again, that's in the other things that I have linked to. But the point is that light has to be disturbed by something else if it is to wave. If it could wave, if you have a bowl of light that can be disturbed, but that doesn't seem to be the quality of light or any other EM wave. It seems to be emitted from a source, and it can go through vacuum fields or vacuum tubes. For example, the old TV sets used to have vacuum tubes, and they made light that you could see. So light travels through a vacuum. That means there's no medium. So that's why people came up with things like ether, or now they call it quantum something or other, quantum fluid. They're trying to call ether by different names. And the thing is that they're saying that there must be some other medium in order for us to see light in a vacuum. And as I explained in the other videos, if something doesn't have a medium, it has to be its own medium, like a slinky, where, if you hold one end and you stretch out the other end and then put it back and stretch it out and put it back and make an oscillation, you'll get like bands of compression and rarefaction, they call it, in any kind. It's called a longitudinal wave. And the thing about a slinky or any other spring-like thing, if you have a longitudinal wave, you still have the spring itself attached at both ends and compressing and stretching. So how does light do that? How do you do that with an electromagnetic wave? Is it attached at both ends somehow? That really is stretching it, pun intended. So light and EM waves are mysterious and hard to wrap our minds around, but we shouldn't invent things like ether just to try to explain how light can travel without a medium. But it does travel. It has speed. That's all we know. And that's all I wanted to say, is to explain that the speed of light, which can vary, is the only way I can think of to explain how it behaves through lenses, through changes in density. So that's it. That's all I got. I'm going to stop there. And thanks for coming. See y'all later.